we are going to solve a problem on node analysis. A circuit is given here. Write the node voltage equations and find the current through each branch. So this is our circuit, and we know what are the procedures for solving a circuit using node analysis. So first of all, we have to identify the reference node and assign 0 voltage to it. So here this will be the reference node. It will be having a voltage 0. So reference node means this point, this point, this point and this point together. It is the reference node. Now identify the various multiple nodes in the circuit and assign voltages to those nodes. So here the multiple nodes are, this is a multiple node and let its voltage be V1, and this is another one, let it be V2. So we have identified the reference node as well as two other nodes. Now mark currents to all the branches which are meeting at the considered nodes. So here at node 1 there are 3 branches. So mark currents to all the branches, and while marking the currents, mark all the currents as they are leaving from the node. Mark all the currents as leaving currents. So here there are 3 branches, branch 1, branch 2 and branch 3. So here, so there is a point, an important point here. If there is a current source in a particular branch, this is a current source. So if there is a current source present in a particular branch, we need not have to represent a current in that particular branch, because a current is already given there and its direction is also given. Okay, so a current is already there and its direction is also given. So we don't have to mark a current in a branch where there is a current source. So we don't have to mark current here. So now let us mark a current in this particular branch and let it be I1. Okay, and current flowing through this branch can be marked as I2. Okay, now for this particular node, node 2, there are 3 branches. So mark this current as I3, this is I4 and this is I5. Okay, so we have considered the multiple nodes, assigned voltage to those nodes, and also we have marked the currents flowing through various branches. Now let us apply Kirchhoff's current law to each of the considered branch nodes. So consider node 1. So we are considering node 1 and apply Kirchhoff's current law to node 1. And we know Kirchhoff's current law, that is sum of currents entering into a junction is equal to sum of currents leaving from the junction. So look at node 1. So there are 2 currents which are leaving from the junction, and see this current and the direction. The direction is marked like this, that is this current is moving like this. So this current, 5 ampere current, is entering into the node. As direction arrow mark is shown as upwards, this particular current of 5 amperes is entering into the node. So according to Kirchhoff's current law, we have sum of currents entering into a node is equal to sum of currents leaving from the node. So here leaving currents are I1 and I2. So sum of currents leaving, that is I1 plus I2, is equal to sum of currents entering, that is 5 ampere. Entering current is given as 5 ampere. So I1 plus I2 is equal to 5. Now let us write expression for the branch currents I1 and I2. See, I1 is the current flowing through this branch. So current I1 will be equal to, I is equal to V by R, that is voltage across this branch divided by resistance of the branch. Now voltage across this branch means potential of this point minus potential of this point, that is V1 minus, this is a reference node and potential is 0. So V1 minus 0 divided by resistance of the branch is 10 ohm. Okay, plus I2. I2 is the current flowing through this branch. So that value of I2 will be equal to potential difference across the branch or voltage across the branch divided by resistance of the branch. So voltage across this branch is potential of this point minus potential of this point. That is V1 minus V2 divided by the resistance. So I2 is V1 minus V2 divided by resistance of the branch is 3 ohm, which is equal to 5. Now simplify the equation. So this will become, I am going to take V1 as common outside. So V1 into 1 by 10 plus 1 by 3. V1 into 1 by 10 plus 1 by 3 minus V2 divided by 3 is equal to 5. Now rearrange the equation. Keep all the variable terms containing V1 and V2 on the left hand side and all the constant terms on the right hand side. So 1 by 10 plus 1 by 3 becomes 0.433. So this will be 0.433 V1 minus 1 by 3 is 0.333. So 0.333 V2 is equal to 5. This will be our equation number 1. Okay, I am taking equation number 1 here. 0.433 minus 0.433 V1 minus 0.333 V2 is equal to 5. Our equation number 1. So now let us consider node 2. So consider node 2. See, this is our node 2. So there are 3 branches meeting at node 2 and all the currents I3, I4 and I5 are leaving from the node. Then according to Kirchhoff's current law, sum of currents entering is equal to sum of currents leaving. So there are no entering currents here. So we can write sum of currents leaving is equal to 0. Or I3 plus I4 plus I5 is equal to 0. I3 plus I4 plus I5 is equal to 0. Now let us write equation for I3, I4 and I5. See, I3 is the current through this branch. So that will be V by R. I is equal to V by R. That is voltage across this branch divided by resistance. So voltage across this branch is V2 minus V1. While we are considering a particular node, always assume that the potential of that node is the higher. The node that we are considering is having a higher potential. So while writing the expression for node 2, we have to write the voltage across this branch as V2 minus V1. Whereas in case of V1, if we are considering node 1, assume V1 is the higher potential. So voltage across this branch will be V1 minus V2. So when we are considering node 2, write the voltage across this branch as V2 minus V1. So I3 will be V2 minus V1 divided by 3 plus I4. I4 is the current flowing through this branch. So V2 minus 0 divided by 5 plus I5. I5 is the current flowing through this branch. So potential of this point minus potential of this point. Okay. So here current is flowing I5. Current I5 is flowing from the positive terminal to negative terminal of this battery. So voltage will be V2 minus 10 volt. Okay. So V2 minus 10. So that is the voltage across this branch divided by resistance of the branch is 1, which is equal to 0. This is the KCL equation. Now let us simplify the equation. Okay. So let us simplify the equation. I am taking V2 as common outside. It will be V2 into 1 by 3 plus 1 by 5 plus 1. Minus V1 into V1 into 1 by 3 minus V1 into 1 by 3 minus 10. Taking minus 10 to the right hand side, it will be plus 10. So all the variable terms on the left hand side and the constant term is on the right hand side. So now solve 1 by 3 plus 1 by 5 plus 1, that will be minus 1.533. 1.533 V2 minus 1 by 3 is 0.333 V1 is equal to 10. This is our equation number 2. Okay. So we have 2 equations and 2 unknowns. Now let us solve these equations using Kramer's rule. So let us note down our second equation here. 1.533 V2 minus 0.333 V1 is equal to 10. So for solving these equations using Kramer's rule, we have to represent the equations in a matrix form. That is, a coefficient matrix into the voltage matrix is equal to a constant matrix, that is our current matrix, or 1 by R into V is equal to I is equal to V by R. So first matrix, the coefficient matrix, is the this particular matrix contains the coefficients of V1 and V2 in equations 1 and 2. So first of all, let us write the coefficient matrix, and first row of the coefficient matrix will be the coefficients of V1 and V2 in the first equation. So looking at the first equation, the first row, first element will be coefficient of V1 in the first equation, that is 0.433. Second element is coefficient of V2 in the first equation, that is minus 0.333. Now second row is from second equation. Second row, first element is coefficient of V1, that is minus 0.333, and coefficient of V2, that is 1.533, into V1, V2, unknowns, that is V1 and V2, which is equal to the constant terms on the right hand side, that is 5 and 10. Okay, so this is the matrix representation. Now we can calculate the unknown voltages V1 and V2 using Kramer's rule. Okay. Okay. So by Kramer's rule, the unknown voltage V1 is equal to delta 1 by delta, where delta 1 is the determinant of that matrix, which is obtained by replacing the first column of the coefficient matrix by the current matrix. That is, replacing this first column, we will get replacing the first column by this constant matrix. So first column becomes 5, 10. Second column as such, minus 0.333 and 1.533. Determinant of this matrix divided by delta is the determinant of the original resistance matrix, that is 0.433 minus 0.333 minus 0.333 and 1.533. So calculate these two determinants and take the ratio of it. We will get the value of V1 as 19.886 volt. So this is the value of voltage at node 1. Now calculate V2. So V2 is equal to delta 2 divided by delta, and delta 2 is the determinant of that matrix. Delta 2 is the determinant of that matrix, which is obtained by replacing the second column of the coefficient matrix by the constant matrix. So it will be first column as such, that is 0.433 minus 0.333, and second column, instead of second column, write the constant matrix, that is 5, 10, divided by delta, that is determinant of the original resistance original coefficient matrix. and answer will be, the value of voltage at node 2 will be 10.84 volt. Okay, so we got the value of V1 and V2, voltage at node 1 and node 2. So we have been asked to calculate the node voltages, to write the node voltage equations and calculate the current through each branch. So we have to calculate the current through the different branches. Okay. So let us calculate the currents. So for that, let me draw the circuit again. 5 ampere. 10 ohm. 3 ohm. 5 ohm, 1 ohm and 10 volt. So this was our circuit, and this was current I1, this is current I2, current I3, I4 and I5. So various branch currents are marked here. So this is one branch current that is already given as 5 ampere. So calculate the remaining branch currents. So for that we have I1 is equal to, I1 is V1 minus 0 divided by 10. V1 minus 0 divided by 10. And we have got V1 as 19.886 volt and V2 as 10.84 volt. Okay, so I1 will be V1 minus 0 by 10, that is 19.886 divided by 10, which is equal to 1.9886. Okay, now next current is I2 ampere. I2 is V1 minus V2 divided by 3, which is 19.886 minus 10.84 divided by 3, which is equal to 3.015 ampere. So this is I2. Now we have to calculate I3, I4 and I5. So if I2 is 3.015, I3 will be minus 3.015, because I2 and I3 are the currents flowing through the same branch, and we have marked those currents in opposite direction. So if we got I2 as plus 3.015, I3 will be minus 3.015. So we can write I3 directly here as minus 3.015. So that means I3 actually flows in the opposite direction, that is in the direction of I2. This is the correct direction for current. So next is current I4. So I4 is V2 minus 0 by 5, that is 10.84 divided by 5, and that will be equal to 2.168 ampere. And last one is I5. I5 is V2 minus 10 divided by 1, which is equal to 10.84 minus 10, which is equal to 0.84 ampere. Thus we have calculated the currents flowing through all the branches of this particular circuit.